capacitor. This is AC circuit we are talking. Okay, this is called capacitive reactance. Now girls, so question would be like that: the reactance of this much of capacitor when a frequency of 15 kilohertz is applied. So just put the value of C and F 2 pi, you will be getting the reactance. Okay, and reactance will be 226 ohm by putting this value. All right, this is capacitive reactance. Now girls, reactance, as I said, it is same as the resistance. So girls, when you are having capacitors in series, please watch carefully. When the capacitors are in series, the total reactance is the sum of the individual reactances. Yani, it is same as you add the resistances when they are in series. Remember, T is equal to R1 plus R2 plus R3, like that. But when the capacitors, the total capacitance you want to calculate in series, the formula is this one. Remember this also? Correct? So don't confuse with that. This is total capacitance when the capacitors are connected in series. And this is what? Total reactance when the capacitors are connected in series. Because as I said, capacitive reactance is similar to the resistance, and when resistance are connected in series, you know the formula. Is it clear to all of you?
Yes, it's clear.
All right. So this is, you need to relate the things with the previous. Now assume this much of capacitors are in series with this much of kilohertz AC source. What is the total reactance? So it's so simple. Either you calculate first reactance, okay, of 1 and then multiply by 3 because they said 3. All right. Or what is that? You calculate the total capacitance because they are 3 capacitance in what they are in series. So either you can use this formula, which one? Reciprocals of the sum to get the first, this one, 1 over C1 plus 1 over C2 plus 1 over C3. After getting this one, you can say XCT, which is gonna be 1 over 2 pi FCT. Is it clear, this formula? One approach. And second approach, you just calculate C1 for any capacitance, yeah, right? Or just say C because it's just a single capacitance. All values are same. 1 over 2 pi FC you will be getting here. After getting this C, what I will, sorry, it's not C, sorry. This is XC, huh? XC. Yeah. So after getting this one, I can say XCT total, which is gonna be what? XC1, XC2, and XC3. Okay, by the way, C is in the suffix. Or you can say 3 XC. Clear? Because same. So whatever you feel it's okay for you, you can go this way. So you can calculate it. See the solution now, how they calculate. I believe they calculate first the XC simple, which is 1.93 kilo ohm. Now they are connected in series, so total reactance is gonna be just sum or multiply by 3, 1.93. Answer is 5.69 kilo ohm. Clear? 79 kilo ohm. This is capacitive reactance. All right. Any doubt? Any question here?
No, it's clear.
Okay. So capacitive reactance is gonna be treated as resistance. Similarly, girls, capacitive reactance when capacitors are in parallel. So it is same formula which you use there. Reciprocals of the sum of the reciprocals. Correct? Also, when two capacitors are connected, and now again, if the this much of capacitors from the last examples are placed in parallel with 2.5 kilohertz AC source, what is the total reactance? So how can we go for this? To approach again, which is the easiest one this time, you know? Can we calculate CT? They are in parallel. So when capacitors are in parallel, the formula of the total capacitance, remember guys?
Yes.
Yes.
So can I calculate this way?
Yes.
Correct. Now after that, XCT is equal to 1 over 2 pi FCT. Just quickly calculate this one. F is 2.5 10 raised to power 3 and CT is given 0.099 10 power minus 6. Kindly calculate it and check it. How much is there?
Uh, 643.05.
Okay, and it is gonna be what is the unit?
Ohm.
Ohm. All right. This is the answer. Okay, now see how they are calculating here in this. So 643.05 and see this approach. So they calculate first XCT this way, right? This is the, because they already know XCT 1.93, so they just apply the formula, one of the reciprocal, that one. So it's up to you how you want to calculate. First calculate the capacitance or directly calculate this one XCT. Hope you clear, hope you have idea of what I want to explain in the previous examples. We have different approaches. So this is capacitive reactances, girls. Class now. So okay, how many slides are remaining here? Let me just check. Still there are many. Okay, so we can, let's see, inshallah. So what I was explaining, this is capacitive reactance for the series which we done. Next one is for the parallel, which we have discussed. Now see, this is the interesting thing here. So we can have a circuit where we have only capacitors, they are connected in series. So if you look here, it looks, it resembles the one which we have discussed earlier, which I draw also here. Like if you remember this type of divider circuits we have discussed earlier, like this is R1, this is R2, right? So now this is for the capacitive divider circuit, though it is a series divider circuit. So two capacitors in series are commonly used as a capacitive voltage divider. The capacitors split the output voltage in proportion to their reactances. How they split the voltage? In proportion to their reactance and inversely proportional to their capacitances. You know that this one also. So proportional to their reactances, girls, if I ask you how much is the V out? So the way is that either, do you remember if I ask you here V out in this case, what will you write? You always write V out is equal to R2 over R1 plus R2 multiplied by Vs, if this is Vs. Clear? Is it clear to all? You know this one, right? Now, same formula you can write for this capacitive reactance. How? This is, let's say, XC1. Let's suppose this is XC2. If we know, I don't have, if I know. So I can write the formula V out is equal to XC2 over XC1 plus XC2 multiplied by Vs. Did you get it?
Yes.
Understand this point? Yani, if I know the reactances formulas which you learned earlier, it is gonna be same. But if you wanna calculate with the capacitances, so formula is gonna be what? Not XC this time, C1 over, because what they said, yeah, C1 over C1 plus C2 multiplied by Vs. Like a current divider formula. Do you remember? Like a current divider. This is gonna be this way. So both will work. But which you wanna use it, you have to go accordingly. So now, sorry, this is not C1 plus C2, girls. It should be what it should be? CT. What was that? We have discussed this formula earlier. Just go back. Let me see this one. Yeah, maybe a little bit confusion. series, yes, this one. CT over CX into VS. This is the formula. Voltage divider. So let me correct it. So if you wanna use the voltage divider, so one formula is this one. Just reach there now. Okay, this formula. Where is that question? This one here I was discussing. So this formula I can write simply CT over C2 multiply by VS. Is this like that? So both formulas will work, either this or this. You can use it. So which you want to use, it's up to you. So let's see now the solution, how they are solving. So first of all, we need to know the X1, XC1, yani reactances, if we want to apply this formula, this one. Okay, I'm using red color now. So get it first XC1. Similarly, you need to get XC2. Okay, after getting XC1, XC2, we can apply the formula. We get it XC total first, which is 5.30. And then finally, we can have this formula, which is similar to the resistive divider circuit formula, XC2 over XC total, which is 482 over 5.30. And we will be getting, this is 91 millivolts. So this is 1 volt. Here we out, we will be getting 91 millivolt or 0.019. Is it clear now? How to get this voltage here? By knowing the capacitive reactances. Okay, any question? And you can also apply another formula, VS formula. Are you listening or not?
Yes,
Yes, we're with you, doctor.
Okay, I thought maybe everyone silent now. So this is right. Okay, so we can go this way. If you want to apply another approach, you can see in this question. So another approach is also there. So in this question, again, similar question, what is a voltage across C2, right? So you can say this is a series circuit. They are asking C2. So girls, let's see with another approach, this one. Okay, where we know this formula, which is V2 is equal to C total over C2 over VS. So here you don't need XC total, you can directly see. Now this is the point here, girls. Yani, how can you save your time? I am interested to know the voltage across C2. So if you go this way, you must know XC2, XC total. Then you have to calculate this one. But if you apply this formula, you need C total first. But by the way, these two capacitances are in series. And how to calculate the C total? Can you tell me the formula for C total when they are in series?
Yes, a 1 over 0.01.
No. This is the point. Yeah, it is like opposite formula for the resistance. Do you? That one, product over sum, right? So this is the chain. That's why I said what I said. You just need some practice, then inshallah you will be able to get it. So you need to get it CT first. Then you can apply second formula. So C total will be calculated this way. Then you will be applying, and then you will get the answer. But if you apply first one, so you have to calculate XC1, XC2, then XC total is gonna be sum, because it is treated as the same as resistances. All right, so do some practice of maybe, because you people are having an examination, but before the next, inshallah, you will be just practice it, and you will know more about this thing. Now, capacitive phase shift, which is again very interesting. Like if we have a circuit and in which we are having a capacitor. So there is a property of a capacitor. What happens? See, when a sine wave is applied to a capacitor, sine wave, okay? So there is a phase shift. Yani, this is a property of a capacitor. When you apply a sine wave to it, it produces a phase shift in the voltage. So there is a phase shift between voltage and current, such that current always leads the voltage by 90. And this one can be asked in multiple choice question or somewhere. Very important point. So what is that? The current leads the voltage by 90. See, so if this is the voltage, girls, okay, across the capacitor, So current will lead yani start early, you know that, and touching the positive axis. So it is something yani it is starting somewhere here advance. So this is a 90 phase shift. So if we just get this difference, this is the phi here. Okay, sometime, you know, just to give you confusion or just checking your knowledge, can I say current is, you know, current is always leads the voltage by 90? Can I say voltage is lags
Yes, you can. Lags current by 90.
clear? So we
Yeah.
can read opposite also, any voltage lags the current by 90. Okay, it's just to confuse sometime. So once one thing is clear to you, yani it is clear to you, current always leads by 90, you know, leads the voltage by 90. So concept has to be clear. I can also ask in the reverse order. And same concept which you are learning for the capacitors, girls, it is gonna be opposite for the inductor, which is gonna be next chapter, inshallah. So just understand first, then we'll see what is next. Okay, then power in capacitor. So it is again interesting. Now, what is that? Energy is stored by the capacitor during a portion of AC cycle and returned to the source during another portion of the cycle. You know that. Yani once it is charging, it is consuming. Another half of the cycle when come, it returns. So what? Voltage and current are always 90 out of phase. For this reason, no true power. This is important. No true power is dissipated by a capacitor, because in half cycle it is storing energy, in another half cycle is returning the energy, so it's not consuming the power. That's why we say no true power is dissipated by a capacitor, because stored energy is returned to the circuit, you know that one, right? So that's why no true power. So the rate at which the capacitor stores or return energy is called reactive power. The unit for reactive power is VAR. Which power capacitor store? It is called reactive power. Okay, energy. The rate at which capacitor store or return the energy is called reactive power. The unit of reactive power is VAR. This is also asked, important, volts, ampere, reactive. And how do we calculate this one? You will see this one. So these are the formulas, simple. To calculate the reactive power of the formula, you know that PR, VRMS, IRMS. PR, VRMS square over XC. So we will not use C, you know that. We will use reactive, like what is the equivalent in resistance? XC. This is the formula. PR, I square into RMS, XC. So this one will give you the power, and this is VAR. Volt ampere reactive is the unit of the power. Maybe we have a question for that to understand this point. So determine the true power. If I ask you true power, girls, what should be your answer? Straightforward. True power. I just explained to you. Capacitor does not dissipate any power. So true power is always 0. Is it true or not? Correct? This is
Yes.
0.
Yes.
But it has reactive power. So for the reactive power, we can use any formula. Okay, so just use the reactive power formula. So true power is 0, and reactive power we need to calculate XC. So here we need to spend some time to calculate XC all the time. Then PR, VRMS, because we have given already root mean square. And for the AC source, we always use VRMS. You know that one. So VRMS square over XC, and this way we'll get this one because of 10 power 6. So it is going to be micro. So 503 micro VAR, and the unit is very important. It is not going to be watt this time. It is VAR because of reactive power in capacitor. This is something new which you can highlight. Okay. So this is, I think we have done with that, and this is some key questions which you can go through, girls. And okay, if you want to see this one, okay, go through. The capacitor of a capacitance will be large if